Good evening, ladies and gentlemen. How's everyone doing tonight? Good. I'm well. Thank you for asking. Thanks for coming out to visit us tonight. We're absolutely grateful for your participation and interest. Like the Mars rover, Charles Elachi's curiosity knows no bounds. In his 46-year career at JPL as a world-leading researcher in radar science and eventual director of the Jet Propulsion Laboratory, he has spent his entire career as a modern-day Magellan. With the landing of the latest rover in August 2012, he oversaw one of the most challenging engineering feats since the Apollo moon landing. To quote him from a post-landing press conference, "I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things, even though we might fail, than to stay in a twilight that knows neither victory nor defeat." And the team brought us victory. Yeah, they did. Tonight, Dr. Alachi will discuss that particular victory, his storied career in space exploration, and the remarkable work that JPL is doing as it monitors its existing 19 spacecraft across the solar system and prepares for the next generation. Some additional details about our esteemed guest. From 2001 to 2016, he was the director of the Jet Propulsion Laboratory. He is currently a professor of electrical engineering and planetary science at the California Institute of Technology. In his career at JPL, Dr. Elachi was a leader in developing the field of spaceborne imaging radar, the principal investigator on numerous research and development studies and flight projects sponsored by NASA, and he is currently the team leader of the Cassini Titan radar experiment and a co-investigator on the Rosetta Comet Nucleus Sounder experiment. He is the author of over 230 publications and the holder of several patents. The recipient of numerous honors, he was named one of America's best leaders by U.S. News and World Report and the Center for Public Leadership at Harvard University's Kennedy School of Government in 2006. He also has an asteroid named after him in recognition of his contributions to space exploration. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Charles Alachi.
Thank you. Thank you. Thank you very much for the nice introduction, and good to see all of you here. When you think about it, for literally thousands of years, our ancestor kind of looked up at the sky and wondered about all these stars, what's on them, how they came about. And particularly, they noticed that some of them actually do move, and these turn out to be the planet. And one of them was a little bit more reddish than others, which was Mars, and people wondered what's on that star. And when you think about it, also even a few hundred years ago, we didn't know that there was a Uranus or a Neptune. We didn't know about the rings of Saturn. We didn't know about the satellite around Jupiter. And here in one generation, we have visited each and every one of those planets. When you think about it, isn't that amazing that we have done what's in one generation, what people have dreamt about for thousands and thousands of years in one generation? Not only we visited them, but on some of them we have rovers, some of them we have landers, some of them we have probes. So what I'm going to do today is to kind of describe to you, why do we explore? Why is it something really exciting? What have we learned? And what are some of the future things that we are planning to do? What is the future holding, for particularly this great institution, which was a lead, players in making that happen. Now, before I start on that, I thought, because I always get asked question, how did you end in this field? How did you end coming to JPL? So I thought I'll start with one or two charts, to kind of tell you a little bit about my background and when did I get involved in space. So you look at that picture to the left, that kid who's kind of looking like a little bit upset, that's me. And maybe that was my first experience with space, because my mom dressed me like an angel, because it was my brother's first communion, that my brother is a guy in front of me. And I was very unhappy because I was dressed in a dress instead of pants. So I used to hate that picture, but now I love it. So that was my first introduction to space. I was born in Lebanon. Then I did my undergraduate education in France, so you see that in the middle. Then I came to Caltech for my graduate degree, and at the right, that was my first team here, and I see one of them is here, Joby. Where are you, Joby? There you are. So she's the lady sitting with the red dress. So you can see when I was younger, I used to have a mustache. I used to have a lot of hair. When I showed the picture in the middle to my younger daughter, she kind of slipped. She said, Dad, you used to look pretty good the day before. I told her, what do you mean? I said, oh, sorry, but now you are very distinguished. So she corrected herself very quickly. So anyway, so I did my undergraduate at Caltech and started working here at JPL as a summer student first and as a part-time academic, like many of the people sitting here. And then I was offered a job. I said, gee, I'll work here for a couple of years, and 48 years later, I was still here. Now, let me go to the original topic of about, when you look in the sky, I'm sure you can count hundreds of stars. But in reality, when you look through a telescope, particularly a telescope like the Hubble telescope, you'll be amazed of how many stars and galaxies are in the sky. This picture here, which was taken with the Hubble telescope, that corresponds to an area about the size of a dime at the end of your hand. That's about the area that you see in here. And literally, you are seeing billions and billions of stars and galaxies. So when you think about it, it's an amazing universe that we live in. And if you zoom in a little bit on that picture, so you see some of the galaxies, and it's a very active universe. So you see actually galaxies which are interacting, you see stars which are forming, you see stars which are basically dying. So we do live in a very active universe. And somehow in one of those galaxies, it's kind of similar to our Milky Way galaxies, around one of those little stars, we had planets. Somehow they came about. And this is our solar system. So you see the Earth and Mars and Venus, and somehow on one of those planets, there was all the right ingredients, the right temperature that basically led to cells which formed, and those cells led to the life that we are familiar with. So when you think about it, it's amazing. How did it start from the beginning of that universe about 14 billion years ago? And here we have people like you and I, sitting down having this conversation tonight. So don't you wonder how did that came about? And particularly on our planet, after 3.8 billion years of evolution, guess what it produced? It produced JPL. So people don't appreciate that JPL took it 3.8 billion years to actually evolve and be where we are here. And more important, the employees at JPL, through all that evolution, had a certain attitude. Guess which one in this picture? There is one guy who's a JPL employee. But the point I want to make about this picture, this is from the early days of JPL, is while everybody is looking in this direction, the JPL employee is looking in that direction. And that has a meaning behind it, because we don't go where other people go. We try to look at things differently. We look at things out of the box, and we are looking at things that nobody else looks at, and we try to make them reality. Now, one thing I want to make sure for particularly the young JPL employees here, don't try to come with that dress code. That's not the normal dress code, So now what I'm going to show you, just looking at the last 15 years, actually what this great institution has accomplished. So I'm going to show you a very short video which show you about every launch and every activity and every encounter which happened just in 15 years. So if we can get that video on. fantastic demonstration of what our nation and our agency can do. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in a twilight that knows neither victory nor defeat. And the team brought us victory.
I just wanted to call and say congratulations to the entire Mars Science Laboratory team and really all of JPL. You guys should be remarkably proud. And this is the kind of thing that inspires kids across the country.
Anyway, when you think about it, it's amazing. It's amazing what our nation and this institution has done in the last 15 years. Usually when people ask me, how many employees are there at JPL? At employees, we don't have any employees. We have 6,000 explorers, because that's what people actually, do here. And the other thing, I didn't come up with this title about the golden age of exploration. I was showing this video to Jim Cameron, who's the ultimate storyteller. And at the end of it, they said, this was a golden age of exploration, when he saw that thing. So now what I'm going to do is to tell you a little bit about some of these missions. I cannot go through all of them, otherwise you won't go home tonight. So I'm going to start by talking about probably one of the most exciting, and in many people's mind, the most exciting missions that JPL is conducting, and that's the Cassini mission. And the Cassini is not just spacecraft which visited Saturn, but it really explored over a period of almost 13 years, explored the whole system, which is around Saturn. Now, Saturn is a beautiful planet. Everybody knows about it because of the rings, and they look great. And you see that's a more detailed picture, of the rings. But there is more fundamental reason for exploring Saturn, is because by analyzing the rings and understanding the satellites around Saturn, it shed light about how our own solar system actually formed. One of the key theories about the formation of our solar system is when a dust cloud collapsed and formed the sun, there was a lot of dust around it, so there were rings around it, and the particles in those rings agglomerated together, and they became rocks, and they became bigger rocks, and they became the planets that we are, on them. So by watching Saturn rings, it could give us some insight about how our own planet and how our own solar system actually formed. Now, to make you believe me, you can see in that picture what looks like a small satellite is forming just at the edge, of that ring. And if you zoom a little bit more in some other one, you actually see in those gaps that you saw on Saturn, actually small satellites is forming. So it's in a sense, we're doing an experiment by watching, Saturn It's like you are in your lab doing an experiment of forming a planetary system. And that's actually what's happening, on Saturn. Of course, our solar system took many billions of years to form, and here we have been watching it only for 14 years, but it gives us some idea about it. Now, just to tell you about some of the major discovery, this is a satellite of Saturn called Titan. It's about the size of our moon. It's a very big satellite. It has cloud all around it. But what's amazing, and it has about the same pressure as the Earth here. So if you are on Titan, it's about the same pressure, but the atmosphere is mostly made of methane and hydrocarbon, and it's much colder than here. But when we looked at it in more detail, we actually found something very similar. You look at the picture on the right at the South Pole on Titan, and it has lakes on it. And these are lakes which are the size of the Great Lakes. So actually, if I show you a series of pictures, actually it looks like it rains on Titan. Liquid goes into rivers, the rivers go into ocean, then they evaporate, they go up in the atmosphere, there are clouds. So it's very similar to our own planet, except it's all made of hydrocarbon. The rain is not made of water, it's made of kind of gasoline, if you want. So I keep jokingly tell people, if you live on Titan, you don't need to go to the gas station. You just go to the nearest lake and take a bucket and you can fill your car, with it. And then on the picture to the left, we saw it's desert, sand dunes, similar to what you see in the Sahara, in the tropical or in the dry, arid regions around our planet. So here you have a satellite which have a lot of similarity, not identical, but a lot of similarity to our own planet. And a number of scientists believe that it could be a prebiotic planet. That means a planet which have organic material, and maybe it was early way of how life started. And some people think there might be life different than ours, which doesn't require water. Actually you can, but you have all the hydrocarbon which exist on it. So now we're starting to think about future missions of possibly put boats in those lakes, go sailing, possibly balloons in the atmosphere to explore it more in detail, rover on that planet. So this is one example of the kind of things that we'll be doing, or our nation and NASA will be doing over the next couple of decades. Another interesting satellite of Saturn, this one is much smaller, it's called Enceladus, and it's all made of ice on the surface. We know that from what we call spectroscopy. But what was very puzzling is you see those blue stripes, at the bottom. So when we flew by those blue stripes, also on Cassini, by using what we call a thermal infrared instrument, which measures the heat, we find that those stripes actually are warmer than the environment around them. So that was very intriguing. But then Cassini looked back toward those stripes, and we actually saw geysers shooting out of those stripes. So it's like you are up in Yellowstone, and these geysers are shooting up, except these geysers are like 50 kilometers high. So they are higher than when you are flying on an airplane. You will see geysers shooting up. And being the typical JPLs always look in the different direction, actually the team here, which was an amazing team, actually targeted Cassini to fly through one of those plumes, and they found that actually it's water ice and it has organic material in it. So now one theory is that possibly these geysers are coming out from an ocean below that ice, which is liquid, and then as soon as you say in liquid ocean of H2O, then people will immediately say, could there be life in it today? Now you will say, well, but Enceladus is way out. How could it be liquid water in it? Well, it turned out as Enceladus goes around Saturn, you have this big planet and it creates tides. So you have the ice is being pumped back and forth for billions of years, and that generates heat, and that's what melted the ice below the surface. So now one mission people are thinking about is actually to go fly a spacecraft which will go fly through those plumes, collect samples, and possibly bring them back to Earth. And then you can analyze the composition of those samples. So that's another example of these far-out missions that we're thinking about. Now, this one is one of my favorite pictures. This is a picture of Saturn taken from Cassini when it was behind Saturn relative to the sun. So Saturn was blocking the sun. And when you do that, you can see very faint light around it. So it's the same. Now I barely can see you because the light is in my face, but if I block it, I can see you much better. So basically from that picture, actually what you see, those two little dots, that's us. That's the Earth and the moon next to it. So that little dot is all of you live on this dot, all your friends, all your neighbors, all the people you like, all the people you don't like, they are all living on that little dot. So that gives you a perspective of our position in this, just in this solar system. Just imagine in the universe. Now, Cassini have been flying for almost 13 years. But unfortunately, in September, it's coming to an end. So it's going to be a bittersweet kind of moment because basically all the fuel on it have been consumed. But again, the imaginative team said, well, we're not going to crash without a big celebration. We're going to figure out a way of how do we get even more science. So they came up with the idea of actually bringing the spacecraft very, very close to Saturn and fly between Saturn and the rings. And I mean, really coming close, to Saturn. And that's what you see is happening as we speak today. We're coming every few days. We're diving between the rings and Saturn itself and getting some amazing perspective, about Saturn and about what exists between the planet itself and the rings. And then on September 15 is actually we'll crash the spacecraft into Saturn. Now you say, why in the heck are you doing that? I mean, this is a great spacecraft. Well, one thing we want to make sure is that once we lose control of it, when all the propellant is consumed and we lose control of it, it doesn't end at some future time crashing in Titan or in Enceladus and carry some of our microbes with it. We want to make sure those satellites are very pristine. So if we go to explore for life in them, we don't find the life that we took with us here. So that's part of the reason we actually will crash it. So it doesn't mean that people are not doing a good job. It just means that we on purpose did that. So that happened September 15, I think at 2:30 a.m. in the morning. The other great mission that is ongoing now is called Juno, and that's a mission going exploring Jupiter. It got there about a year ago. And basically what that mission does, by using microwave radiation, it can probe deep into the atmosphere of Jupiter and see what's the internal composition of that planet. And to do that, it comes and flies very, very close to Jupiter, even in the radiation belt, and then it goes far out and then come back in. And it has a camera on it, and I picked one of those pictures. Look at the amazing picture of what you actually can see. All these basically hurricanes which are happening. Each one of them is the size of our planet. So this is a very dynamic planet. And that will give us insight in actually the atmospheric dynamic and how hurricanes form, how they dissipate, how they interact. So in addition to seeing deep into the inside of Jupiter, also is giving us a new insight about the atmospheric dynamic around it. And these are some of the more recent pictures, that were acquired with that mission. Now, around Jupiter, there is another satellite which is very exciting, kind of like Enceladus, except much bigger, and it's called Europa. And as you can see from that picture, Europa is made of ice. We have known that from Galileo and even from Voyager. And you see that brown material, and when I say ice, I mean H2O ice. It's a thing you put in your drink, and when you're making a martini or something. So it's that kind of ice, H2O. But you see also these fracturing and all these cracks, which are on it. And when you look at it a little bit more detail, what that reminds me at the top is when you fly from here to Europe over the North Pole, you see these icebergs which are floating. So that's exactly what is here. It looks like big icebergs which are floating on the surface. And if you look carefully, you can trace some of those features. You trace them to the edge of an iceberg, and then they are displaced. So that indicates that actually that ice is moving, which implies that most likely there is an ocean below it. And then from measurement of the gravity field and magnetic measurement, people have concluded that actually there is a thin layer of ice, thin meaning anywhere between a few hundred meters to a few tens of kilometers. And then there is a deep ocean below that, which are all made of H2O. So again, that brings the same question: could there be life if there is actually an H2O ocean now? Could there be life actually in that ocean? Again, today, not past life, but life today. So that's the next major mission that's being planned, or one of the next major missions being planned, is a mission to go to Europa, first to put an orbiter around Jupiter, fly through a series of flyby of Europa, and using a very high resolution cameras and a sounder, a radar sounder, determine how thick that ice is and where is it the thinnest. And then shortly after that, we'll be putting a lander on the surface so we can analyze what is that ice made of, how hard it is there any organic material in it? And guess why we're doing that? Because after that, we want to land on it, drill our way down through that ice, and put a submarine in that ocean and see what is that ocean made of, is there life in that ocean? And people are already working on actually what I call a upside-down rover, which are down in the ocean, where actually you put a rover through the ice, the rover floats up and drive at the bottom of the ice upside down. And that's Kevin Hand is one of the scientists here working with a team of engineers where actually they are doing this in Alaska. So they went through lakes which are actually frozen, and they drilled the hole, they put that rover upside down in it, and we control it from JPL here. So this is kind of the early technology that possibly 15 years from now, you probably will read about it, that we're doing that on Europa. Now, so that's one major emphasis that JPL is doing, is potentially looking at present life in our solar system. But also there is a lot of interest on Mars, and Mars has interest for a variety of reasons. One, historic, people in science fiction stories. It's a place where potentially we might be able to travel sometime in the future. But also Mars has a lot of similarity with Earth. It has differences, but it has a lot of similarity also. Mars is about 1/4 the size of Earth. So if you look at the land mass on Earth, if you forget the oceans, that's about the same area as Mars. So it's a fairly large place. It has polar caps. You can see the polar cap at the bottom, in this case. The day on Mars is a little bit longer than a day on Earth, a few tens of minutes longer. The year on Mars is about 2 years, on Earth. Mars has an atmosphere, not as thick as our atmosphere, but it has an atmosphere. And then if you zoom on it, Mars has a lot of similarity. You look at the geology on Mars, it looks very similar. Sometimes I give this as a test to the audience, tell them, guess which one is the Grand Canyon and which one is the canyon on Mars. If I don't tell you, I'll bet you half of you think it's the one on the right is on Earth, half of you will think the one on the left is on Earth. So I will have a test coming up, so hold off. You look at volcanoes, we have volcanoes on Earth, you have volcanoes on Mars. So that's Mount Olympus. It's higher than the Himalayas at Mount Everest on Earth. And clearly, even that now it's extinct, but clearly at an earlier time on Mars when the volcano was forming, there was a lot of volcanic activity happening on that planet. So even that now it looks like a frozen planet or a dead planet, sometime in the past, really it was a very active planet. If you really zoom on the things, this one is a test. I ask people, guess which one is Death Valley and which one is Mars? I give that test all the time to my students. So let me see, how many of you think the one to the right is Mars? Okay, that's a good number. How many of you think the one to the left is Mars? That's a little bit more. Sorry, I forgot. I don't know which one is which. The two look so similar. Now, some of you might have been a little bit perceptive. On the one to the right at the beginning, there was a snake going through it. So that's how I remember that the one to the right is, to your right, is actually the Earth, because there was a snake which was going around it. But the point of this is that the geologic activity which formed Mars are the same as the geologic activity which formed Earth. So when a human go and land on it, an astronaut land on Mars, she will think that she's in Death Valley, doing that. So it's very similar to our planet. And of course, we have now 2 rovers which have been exploring that planet. The one to the left is Opportunity, has been there for 13 years. I kind of lost track, how long. It was supposed to work for 90 days, and then there was a whole bet going on. Some people said maybe 1 year, and everybody thought they are crazy, they don't know what they are talking about. Well, 13 years later, it's still exploring it, and the one to the right is Curiosity. But the interesting thing, particularly about Curiosity, it's basically like a chemistry lab, which was packaged inside a car-sized rover and is now exploring this planet. So it has in it most of the things that you find in a first-class chemistry lab. It has an oven that you can put sample in it and heat it and look what gas coming from it. It has an X-ray spectrometer, which basically similar to what the dentist used to look at your teeth, except a lot more expensive. We have a gamma ray spectrometer. We have a laser beam, which actually zaps the rocks, see what's being emitted from them, and actually make an analysis for it. So it has a whole chemistry lab. in it, and it has a drill which actually drills the rocks and takes samples and allow us to figure out what's in that sample. And that's what the surface kind of look like. For a geologist, this gives a lot of feeling that these are dry lakes. It looks somewhat similar to when you go in the Central Valley or around Owens Valley and you see a lot of those dry lakes. So it has a lot of the similar feature as dry lakes. And when you look at the orbiter data, it looks like there are streaks which happen when the surface warms up. You know, during the summer, during noon, you see actually these streaks coming down. To make a long story short, I mean, the two major discoveries that number one, we believe that in a past time, actually there was liquid water, H2O, on Mars at the same time when Mars formed and Earth formed. So we started very much alike. But then Mars went one way where actually the water went away. Most likely it's frozen below the surface and became much drier, while Earth led to you and I living here. So a key question is, during those first few hundreds of millions of years, could have life started on Mars? If it was very similar to Earth, if it had H2O in it, it had volcanic activity, it had thermal activity going on, could have life started? And if it did, how far did it evolve? And if it did, where is it? And if it did not, why not? Why did it happen here and did not happen on Mars? So that's one of the key objectives that the people on Curiosity are looking for and our future exploration. And you see sand dunes similar to here. Again, I could have told you I just was last week in Saudi Arabia. That kind of looks like Saudi Arabia. And these are some of the more recent images of these sand dunes. It looks very Earth-like, you know, in arid regions. Now, one thing, you know, to kind of maybe impress you a little bit, to show you about the challenge that the people who did this mission had to face to actually accomplish. So I thought I'll pick two examples of the technical challenges to do these missions. So in the case of Curiosity, after we traveled 225 million kilometers, we landed about in an area of about 2 kilometers. Now, to give you an idea what that means if I go outside and hit a golf ball towards St. Andrews in Scotland, the golf ball has to go straight in the cup. That's how accurate it has to be. And to make it a little bit more challenging for the good golfers, the cup is moving. And you still have to get it straight in the cup. So that's a kind of accuracy that people had to do, you know, in the navigation and the technology which had to be developed in the navigation to make that happen. Another example of the challenge is when we arrived at Mars, the energy in the capsule, that means for the technical people here, is 1/2 mv square. That amount of energy is the equivalent of 18,000 race cars going at full speed. And we had 7 minutes to dissipate all that energy and land softly on the surface. So we had to use, you know, of course, we had to use heat shield, we had to use parachutes, we had to use retro rocket, and then finally we sky craned it, landed carefully. In the case of Opportunity, if you notice in the video, it was airbags. And all of that had to work perfectly. And you cannot joystick it because it takes about 10 to 15 minutes for the signal to go to Mars and signal to come back. But you had only 7 minutes, so you cannot sit down and joystick all of this. So now I'm going to show you a video, which I know many of you probably have seen. I've seen like 300 times or 400 times. But it really reflects the spirit of the people here who do that. So I thought you would enjoy, because even after 300 times or 400, I still enjoy it. Matter of fact, my heartbeat goes up every time I watch that video. So that shows you what actually was happening in the mission operation room when we actually landed Curiosity.
Vehicle reports entry interface. At this time, it will begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. The vehicle has just reported via tones that it has started guided entry. Target at this time. We have seen peak deceleration. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating.
Satellite, which
Digital
was observing
separated,
landing.
we're on the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. Standing by for backshell separation. We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky crane. Sky crane has started.
Single eyes, you remain strong.
Touchdown confirmed. We're safe on Mars. Time to see where our curiosity will take us.
Isn't it pretty cool, this movie? And, my wife keeps complaining. She keeps telling you, but Charles, you have shown this movie 300 times. Why are you still showing it? But people love it. And in a sense, it gives an example. All these people there, Adam Stelzner and all the other people, these are the perfect example of that employee I showed you earlier, where nothing stops them. They look in a different direction, what everybody looks. I can tell you, when we first took the concept of a sky crane, to NASA headquarters. We told them that's how we're planning to land the lander. People shook their head and said, "You guys in California must be smoking something that is illegal." Are you kidding us? Is that how you're going to do it? So, but people, explained it to them. Adam and a number of his colleagues explained to them. And fortunately, at NASA, there were a number of smart engineers that said, "Yeah, well, it makes sense. Let's go and try it." And then that's how this all came about. Now, of course, the first thing we did when we landed, or shortly after we landed, we did like all of you do. You get your cell phone, your mom gives you a new cell phone at Christmas or at the holidays, and you go and take a picture of yourself, send it to your mom, say, "Mom, look how good I look." So that's actually what this was. They say, "Hey, Mom, I landed safely, on Mars." Now, what are we doing next on that one? So the next major step is basically we're planning a mission which is very similar to Mars 2020 to certain level. Sorry, it was then Curiosity. So it's a similar rover, except the payload will be completely different. And what this mission will be doing is actually to drive around. It has more sophisticated instrument. Look at samples which potentially could have organic material in them. Collect those samples, about 30 or 40 or 50 of them, and put them in a location where then after we can go land, grab those samples, put them on a small rocket, launch them in orbit, send another spacecraft, rendezvous with them, and bring those samples back. Piece of cake. So that's a challenge for the next generation to do that. Now, to make it a little bit more exciting, we're looking at actually adding a little helicopter on it. So we probably will have a drone which will fly in front of the rover and actually survey the area, in front of it. And that has both aspects. One, it will start opening the frontier of actually doing airplanes and mobility in the air, where you can go a much broader range. But the other benefit is now one of the limitations on how far we drive is every day we can only see from the camera of the rover. So you can only see about 100 meters ahead of you. So you can only plan about 100-meter drive. If you have the helicopter, it can go in front of you and survey many kilometers. And actually, based on that survey, it will show, well, it's more interesting to go here instead of going, in that direction. So it will help actually planning, that the rover activity. And the other neat thing which have evolved because of the technology now is now we have literally hundreds of scientists around the world. They get on their computer and on the phone and try to debate what they should be doing next. By that time, you'll be able to put basically glasses which will actually transpose you as if you are on Mars. So you can walk next to the rover and actually explore. So you'll have hundreds of scientists, around the world actually with those glasses, actually debating and discussing and deciding what should they do. So I can kind of imagine how funny it will be if you see somebody at an airport, in Frankfurt, with those glasses talking about rocks on Mars. I wonder what the other people around him or her will actually be saying. But that's going to evolve completely, how we actually do exploration. Now, let me go to the third topic, which has been a major advance, is not only we are exploring our solar system, but we are starting to actually explore other planetary systems around other stars. 20 years ago, if people would have said, look, there are planets all over the place, people would have not believed you. Matter of fact, I forgot now his name, but there was a monk, which I think in the 1600 or 1700, wrote an article about other worlds and other planets similar to ours. Guess what happened to him? He was burnt on his stake, because people thought that he's kind of lost his mind on it. Well, we're finding today that almost every star has planets, around it. And one of the most recent discovery, which was done with the Spitzer telescope, which is an infrared telescope I've flown, is what's called, it's TRAPPIST, around a star, which is called TRAPPIST-1. Now, I remind people, TRAPPIST, that's not the beer in Belgium. That's actually a star which is in our kind of our neighborhood. And it has about 7 planets about the size of Earth, and a number of them in what we call the region where the temperature is right that water could be liquid. So we haven't detected life, but they are in an environment that's very similar to our planet, the same size, and you have what seem to be similar, temperature, environment. And basically that kind of compare it relative to their star, it compare it relative to our star. So you can see most of those planets are about in our neighborhood or similar neighborhood, and these are to scale. So they are roughly about the same size, as our planet. So that's going to be a very exciting, thing that we need to do next is explore those solar system or planetary system. And the way we do it, you say, well, how did you do that? Now, we didn't have pictures. Those was artists. Basically, what we do, we look at the star and measure, it's, in this case, the heat emission coming from it or the infrared signal. And if you see every once in a while a dip, and then that dip repeat again in a periodic fashion, that means this planet is coming around it and blocking a little bit of that star, and it goes around it. It's kind of simple to do that. So basically, between this mission and Kepler, which I'll show you in a second, basically what we do, we look at the stars, we measure their brightness very, very accurately, like in 1 part per million. And if we see a periodic dip, that indicates there is a planet, which is going around them. And I think the next one illustrates a little bit better, because you can see at the top, when you see those dips, series of dips, and they are exactly periodic, that tell you a planet is around it. You measure the period between the two dips that tell you how long it takes the planet to go around its sun. You look at how deep is that dip, that tell you how big the planet is, because a bigger planet will block more of the light than a small planet. So we can learn a lot by just looking at the dips in the light, of that star. And so far, I lost track of the number, 3,483. It changes every week, it keeps being updated. Probably by now it's even more than that. And recently, not only we were looking at those planets, but we have a group of artists at JPL which developed poster and said, well, let's imagine we're on one of those planets. What would it look like? Or you are advertising travel to go to that planet. So they developed a series of posters which are reasonably accurate. Like the one completely to the right, that's a planet which is around a double star. So if you live on that planet, you see 2 suns in the sky of different temperatures. So one looks a little bit redder than the other one. I like personally the one completely to the left. That's a planet which around a star which is colder than ours. That means it emits mostly in the red and the infrared. So the theory is grass on that planet will be more red color. So here the astronauts are saying, well, it's redder on the other side of the fence instead of greener on the other side of the fence. And this is the TRAPPIST, system, or if you were living on one of those planets, you actually will see 6 other planets, which are around you. So that must be an amazing sight if we live, in that world. Now, the next big challenge, what we want to do next, is not only to be detected there are planets, but actually start taking images, of them. Now you say, how would you do that? The challenge is that we look at a star, it's very, very bright. Again, the same example I told you earlier. It's like I'm looking at some little object next to that light and I cannot see it because it's shining in my face. So what we want to do is to block that light so we can see that planet around it. To give you an idea, that's actually in that glare, it's like having a firefly in the glare, and we want to be able to detect that. So that light is about 10 minus 8 or 10 minus 9, so that's less than 1/billionth the brightness of the star. And the challenge is to develop, telescopes which are perfect, and then be able to do what we call a coronagraph, to be able to block the light, from the star so we can see the planet next to them. And this shows you an example of a concept that's being developed here. So you can have the telescope to your right, and then a smaller spacecraft, which at the beginning it's smaller, separate from it, deploy a huge shade, and then you look across that shade, and that shade will block the star, and then you will be able to see what's around that star, those little planets which are around it. And by detecting the light from the planet directly, then you'll be able to do spectroscopy and determine, does that planet has H2O? That's interesting. Does it have CH4, methane? That's getting really interesting. Does it have hydrocarbon in it? That's getting really interesting. That they have fluorocarbon, the things you have in your refrigerator. Some of these things are basically done by an industrial societies. They don't exist in nature. So that's getting really even more exciting. So that's the kind of thing that people are working on. And these are a bunch of students I'm looking at. I know there are a couple of students here sitting in the front actually developing some of that technology that actually will be flown possibly in the next decade. Now, I'm going to close to remind you that we live on a beautiful planet. People always ask me, Charles, would you like to travel to Mars? And everybody's expecting for me to say, yeah, of course I will. And I give them, no, I think I like it here. It's very nice around here. I love the trees, I love the flowers, I love all the things here. So let me tell you a little bit in closing about what we are doing looking at our own planet. One of the things we have been doing for literally now more than 2 decades is monitoring the height of the ocean. We have been measuring very, very accurately the height of the ocean relative to a frame. And we are seeing that the ocean actually is rising. And you can see it in that picture at the bottom right. And the reason the ocean is rising is that actually ice is melting in the polar region. The temperature is going up, even that some people don't think that that's happening. And actually the ocean is actually rising. And the people who live along the coast, particularly in Florida, 20, 30 years from now, if this continues, their property is going to be below water. Now you say, how do I know that the ice is melting? Well, we actually measure it. We have another mission which actually measures the gravity field, in this case, over Greenland. And by measuring the gravity field, you can determine how much mass in that ice actually exists. And as you see in that picture, in the last decade, actually you see things going down and up, because that's the season. You're going through summer and winter. But on the average, it's trending down. And if you calculate how much of that ice actually has melted and how much the temperature has changed, which will expand the water, when you add those two components, it's exactly what we saw on the previous chart, of the ice. So usually when I talk with people in Washington who are kind of not sure or skeptical, but just showing them those two, slides, actually people become believers. Tell them that actually it's happening. I'm not making it up. It's actually measurement, which is actually happening. And the only explanation is actually that there is warming, which is occurring. Another key application that we have developed to look at here, and I think I saw Mark here earlier, I think he's sitting back there, one of my colleagues down at Caltech, is actually to use satellite images to look at slight motions which are happening on the surface of our planet. So this is like you take a picture today, and then you go home, and then tomorrow you take a picture, and in between an earthquake happened. Don't worry, it's not going to happen tonight. But if something happened, we can actually take those two images, superimpose them, and measure displacement down to centimeter scale. So in a sense, we can get a picture of the earthquake. What you see on the left here is the Napa Valley earthquake, and it shows you the actual motion that have happened. Now, clearly that have scientific benefit, but also it has a practical benefit, because where you see those fringes being very close to each other, that means there was a lot of motion which have happened. And then you can pass that to the rescuers, because most likely that's where there was most destruction, which actually have happened. And this have been used, in semi-operational base, like when there was an earthquake, which happened in Nepal, we just were able to get the data very quickly. And over the next few years, there will be operational system which will be doing this on a global basis. So we'll be able to monitor every day continuously what is changing. Now, there are additional benefits people came up with. They said, well, you know, if I'm pumping water from the Central Valley, the surface actually subsides a little bit because you are pulling water from underground. And actually, you see it in many of the farms. This technique actually can measure how much subsidence is occurring. So you can determine how much water is being pumped out. So that's another example of the practicality of these things. And this is show you that one example. I think this is a dynamic one. We're actually monitoring the changes which have been occurring in Los Angeles. Now, they are amplified a little bit, but actually with this technique, you see actually Los Angeles breathing up and down, and you look at the scale up, that's about 5 centimeters. That's about that much. That actually we are measuring the changes which are occurring due to pumping, which is occurring, you know, from the aquifer, you know, below Los Angeles. Now, let me close by, particularly for the younger people here, to tell you, I told you about how I started at JPL. Now I'll tell you, during the period I was at JPL, it's a great fun. It's a great thing to work here. People think, gee, scientists and engineers, you know, they sit down in their lab and that's all what they work. But now, if you are a geologist or you are doing Earth exploration, you can travel all around the world. To show you some example, up in the left, I was in the Sahara Desert in Egypt, actually doing some work looking at subsurface drainage. The one top to the right, we were looking for the city of Ubar, so we were doing a little bit of archaeology. The one bottom right, we were hosted by some of the Bedouins who were living in the middle of the desert, in the middle of nowhere. And one to the left, actually, you know, there, you know, you have to have people which go with you. It's not like you go to the nearest Earths and you rent a car and then you can go in the middle of the desert. So you have to do a lot of preparation for it. And here I want to tell you a little joke I always like to kind of tell. You know, we were doing an expedition in Egypt a number of years ago. So we had about 30 workers, Egyptian workers, who were hired by the Egyptian Geologic Survey who went with us. And we were about like a couple hundred miles away from any town. So to get fresh food, and we were there for like 3-4 weeks, to get fresh food, you know, they brought with them live ducks. And because it turned out that ducks can support the heat very well. I didn't know that, but I learned it from there. So one evening we were sitting and all the ducks were in the cook tent. So we told the cook, how do you sleep at night? These ducks are so noisy, you know, and they are staying in the same place you are sleeping. He said, oh, it's no problem. Whichever is the noisiest duck, that's what you get for dinners at night. And he said, you'll be amazed, after a couple of nights, the ducks get very quiet, you know. And the other thing, let's see, I think I'm pushing the right button. I think maybe, John, you can, and you meet a lot of great people, you know, that's Cousteau, who came here a long time ago and visited us. You see Prince Andrew, Al Gore. So it is a great place, you know, to work and a great career to do that. And famous movie stars, one thing I tell people is stories. The reason I came to Caltech, I didn't know anything about Caltech other than my professor said it's a good school. But I looked at the map and I thought, gee, it's close to Hollywood. If I go there, I might meet movie stars. I was very much in the movie business. But I didn't meet any movie stars until I came to JPL, you know, and then I became the director. So we had a lot of these movie stars. But at the end, the most important people around you are your family. So I always like to end my talk by telling you I get great support from my family. These are 2 daughters and my son-in-law and my wife and her parents. So I love every evening going home and telling my wife and daughter, you know, guess what? We just landed a spacecraft on Mars today. We just brought a sample, you know, from a comet. So again, thank you very much, and this is truly the golden age. So I guess we have a little time for easy questions. So I think if anybody, you can either have to shout or there is a microphone in the middle there. Go ahead. Don't pay attention to the people who are leaving.
Well, you have a remarkable historical perspective over JPL and all the work of the last few decades. When you first arrived here, what would you say was the spirit of JPL in terms of the engineering and science that was happening, and how has it changed over the years? How has JPL changed versus when you started and as you leave today?
That's a very interesting question. I would say the spirit hasn't changed, but the technology has changed a lot. I mean, the spirit, I mean, you saw that picture I showed earlier about the guy looking, I mean, that was taken in the 50s, I think. And really the spirit here is we are here to explore. You know, we look at what's almost impossible and then we'll go and do it. However, the technology has changed tremendously. I mean, I'm sure you know that. I mean, you look at yourself, probably your cell phone has a hell lot more power than this whole spacecraft, you know, Voyager here. I remember I was giving some kids a tour, you know, here a few years ago, and one of the kids, he said, oh, what kind of, how do you record the data on? I said, oh, well, we have a tape. And I got this blank look, what's a tape? You know, now you put it on a chip. So really the technology has changed in an amazing way. And I think it's going to continue, you know, to change the technology for instrument, the technology of communication. I mean, one example on future mission, we're looking at having laser communication. Instead of these big antennas that you see here, you basically will have a lens, you know, which is a laser. And that will allow you to get a lot more data than we do today. I started in the radar field myself. That's my technical background. I would have never thought we can do what Mark is doing now with this interferometry kind of thing. So it's always, I mean, exploration. That's what exploration is about, is you do things that have not been done before. And what it requires people to be curious, not to be afraid of doing something for the first time, not to hesitate of even if you fail, you know, not to be discouraged, you know, from doing that. I mean, that's how you learn, by doing failure. And on purpose, I think you saw in that video that I showed, there was one capsule which crashed, you know, on the surface. And I do on purpose show it because not everything works perfect. But in fact, if everything worked perfect, maybe you're not trying hard enough. So yeah, that's how you learn from it. And we have learned a lot. You know, if you go through the history of JPL in the early days, I think when we landed on the moon, we had 6 failures before we had 1 success. And average people would have given up, you know, after 6 failures. But we didn't give up, or our predecessors didn't give up, and you see what we're doing, you know, today. So really the world has changed a lot. And I'd love to come 50 years from now and see, you know, what people here will be doing.
Mm-hmm. Do you think that has, back then it seemed that there was a real national purpose. There's such a priority placed on the space program, especially with regard to competing with the Soviet Union, and we don't really have that much today. How do you maintain that sense of national purpose when there's not so much a sense of competition between nations, but...
Get the sense of what, sorry?
Oh, a competition. We don't have the same competition as much between nations as we did during the Cold War. How do you sustain the investment required for the missions going forward? How do you keep that purpose going?
You know, scientists tend to collaborate a lot. Even that there is competition, but competition is done in a constructive way. Because at the end, there are smart people everywhere. You learn from each other. You learn from competition, you know, in doing that, but be it competition nationally or internationally, doing that. And you learn from collaboration. You know, I come up with an idea, and if I talk with you about it, you come up with a little bit better idea. You talk with me, I come up, somebody else comes with a better idea. So the whole area, I mean, in the scientific world, you find that it's not like in the industrial world where I want to beat the other person, or it's really building together and doing that. Now, every once in a while, politics intervene a little bit, but that's the world we live in. But almost every mission you saw here, we had international collaboration, you know, on this mission, and vice versa. There are also, we fly on other, you know, we put instruments on other people, you know, spacecraft.
Thank you very much.
Yeah, well, some of the folks who didn't give up when Ranger didn't work still come around occasionally. I'm thinking of John Cassini in particular. He still visits us, and he's one of the Ranger senior engineers. I'd like to reinforce what you said. I've been coming here for even longer than you've been coming here, and I come and sit down at my desk every day.
Older than me?
Yeah, I've been, on Bastille Day is my 50th service anniversary.
No,
I go to my desk every day and I say, they're paying me to do this? I'm not an employee. But now I have a kind of a narrow, arcane question. The crane for Curiosity flew away and crash landed far enough away for safety. If the crane for the next lander is actually landed carefully with some instruments on it, we can brag that we have put 2 different instrument platforms on a planet with 1 launch.
That's an interesting idea, you know, what you're saying. I mean, we need people to come up, you know, with an idea like this. So in a sense here, if you know, on the next one, I mean, we have the helicopter. So in a sense, you are putting a solid surface platform and a flying platform, on it. You can put the third one. I'm not anymore the director. You might want to go talk with Mike Watkins, about doing that. But on a more serious note, based on what you say, that's how people come up with it. I mean, we need people to come always with what seem to be crazy idea. I mean, my philosophy was when somebody tell me this is a crazy idea, I say, wow, that's cool. Let's go and figure out how do we do it. Because that's how you explore. And it's not unique only about JPL. All explorers in history, that's how they explore, is by really pushing the limit, trying new ideas, trying new ways of doing things, failing every once in a while, learning from it, and then trying again, in doing that. So keep on coming with the new ideas.
Thank you very much for the interesting presentation. My question, are two questions okay?
That's fine. If I say them at the same time, then I think it's only one.
One question is, what are your thoughts on planetary protection? Is it something helpful? To what extreme is it helpful, and when does it become not helpful? Okay. And how would that interact with the future human exploration of Mars, for example?
No, I think that's a very good question. That's a debate we have done many times. I mean, clearly, if you are going to search for life, you want to make sure you are not taking life with you. And also, depending what life you find, you want to make sure you don't bring something you don't like, back to here. So there are all kinds of protocols about cleaning spacecraft, particularly when you have organic doing it. So on Mars 2020, there is a major effort of how to clean the spacecraft, and we have done that on previous missions. And that's exactly why on Cassini, we're going to crash it in the atmosphere, and actually burn it. I shouldn't say crash it, burn it in the atmosphere, because we did not clean it. We were not planning for it to survive for so long on doing that. So we took the planetary protection. Now, having said that, there is a big dilemma of what we are going to do when we send a human. Because you cannot take the human and put them in an oven and heat them, to 1,000 degrees to do that, or use chemical to clean them. So it is a dilemma, on doing that. So sooner or later, we have to accept that we might take some of our life, with us, to other planets. So that is a very legitimate debate to talk about.
And the other question is...
Oh, I thought these were your two questions.
No. And the other question is, what are your thoughts on new space companies participating in future exploration? So
you mean like commercial companies?
Exactly. So like SpaceX talking about colonization of Mars, Blue Origin participating in that.
No, I think also that's a very good question, and it's a very important topic. Basically, at NASA, the role of NASA is to basically push the frontier and do things for the first time. And that's what JPL does, and that's what the government should be doing. Once you develop that technology and you develop that capability, then I think it's the right thing to turn it over to the commercial sector and have the commercial sector make a business, out of it. So many of the commercial companies now who are building rockets, basically they are capitalizing on the technology and the investment that NASA has done over the last 50 years. We are called the Jet Propulsion Lab. We don't do any propulsion. We did that in the 50s and the 60s and developed that capability and then turned it over to industry. Now we're getting companies want to go and do tourism around Earth. That's great. The technology have been developed, the capability have been developed. Someday in the future, the capability of having commercial companies send humans to Mars. But I think still the government has a role to do things for the first time, because you require a major amount of investment to do that normal companies will not do. You have stocks. I'm not sure you have stocks. I'm sure your parents have stocks in a number of companies, and they want to make sure they make profit, for them. And that's what our system is here. So that's where the government should invest and take the high risk activity and develop the technology, then turn it to the commercial sector. So I think you're going to see the future within the next decade, more and more commercial companies actually not only launching, but actually possibly conducting, business if you want, or doing mining or doing monitoring, space. And that's great. That's what we should be doing.
Thank you very much.
Sure.
Hi, very nice presentation. In regard to the Stardust Next mission, is it possible to decontaminate an isotope?
To decontaminate what?
Decontaminate an isotope.
What do you mean? I'm not sure what you mean by decontaminate an isotope.
Okay. Let me explain a bit further. There was a Stardust Next mission
I see.
to a
Okay.
comet, and we tapped the nucleus of a comet, whereby we got some amino acids that were taken and tested in a laboratory, brought down as organic matter, and it turned out that it was carbon-1 being 6 protons and 6 neutrons, and earthly bound. Maybe we got it off of the grid, maybe it was from some other source, but there was also a compound that was 6 protons and 7 neutrons that was very heavy, that couldn't be terrestrial.
I don't think I know how to answer your question. Even that I was a director of JPL, I don't know everything. So I really don't know. I mean, I have to be candid with you. I really don't know how to answer your question.
Okay,
Sorry about that.
but thank you anyway.
I know I'm almost perfect, but not completely perfect.
I understand that if you want to see the corona of the sun, you use a coronagraph, which is simply a disk that appears to block the image of the sun from your perspective. But with the star shield, all the stars other than the sun are far enough away that they're simply a point source. There's no discernible disk because they're so far away. So how do you decide on the size of the star shield and how far away you view from it, and why the pointy leaflets?
Yeah. I think people can figure out there is a relationship between the size of the star shade and the distance, from your telescope, to do that. And there are 2 techniques. I mean, one technique is inside the telescope to put the coronagraphs. That means you put a camera and you put a little dot, in it, which will block the light of the star. But it turned out by putting a star shade a significant distance away from you, you would be able to see even closer to the star. So you can do the geometry, between them. So this star shade, I mean, from memory now, I'm going to tell you, is, many hundreds of meters in size, the one I showed you in here, and it will be many tens of thousands of kilometers away from the telescope. And the challenge, as you could imagine, I'm sure you can quickly think about it, is how do you line them up? Yeah. So your telescope cannot jitter very much. And then your star shade has to be lined up very accurately. But we think we can develop that technology. I think it is within our capability of actually doing that. And then when you move the telescope to look at another star, the star shade has to move and then line up relative to that star. Yeah. So that's how these things work.
Why the pointy ends to the leaflets that we saw in the design that was showing?
So the point in what?
Well, the star shade you show, it looked like it had pointy ends. It wasn't circular. It was roughly circular.
I see that it was not a circle.
It was circle, but then it had pointy ends.
Well, it turned out, if you really do the math and so on, that pattern is the perfect pattern to counterbalance the diffraction that you will get in the telescope. I asked the same question when I first saw it. I said, gee, that looks bizarre. Why isn't it a perfect circle? Yeah. It turned out that when you do the calculation, and I don't have the time to go through it here, and I don't think you'll be interested, it turned out that this pattern is the best pattern to actually block the light from the star and see very faint object next to it.
Okay, thank you.
Okay. Oh, let's see, I think there are, because this thing is being, I guess, transmitted, and there are a couple of questions. Okay, one question is from Cristobal. Which is, what is your vision of the space industry future? And that's kind of the same question that somebody asked here. And again, I think there will be great opportunity in the space business. Now, people tend to underestimate the complexity when people say, oh, we are going to send 1,000 inhabitants to Mars in the next 10 years. I think it's going to take us a little bit longer than that. But I personally do believe that within the next 10, 15 years, maybe 15 years, we actually will be sending humans, to Mars, and that will open the frontier for possible industrial activity. I could imagine doing mining of asteroids. So I think there is an opportunity to it, but it's not a short term. It's not something which will happen, tomorrow. However, what will happen and what is happening now is all the telecommunication industry, all the monitoring industry. I'm sure all of you use Google. People don't think about it twice that actually those pictures, if actually you go from a map to a picture, actually that was taken from orbiting satellite. Many of you, when you watch the news, you see 3D images of Los Angeles and you see clouds coming over it. People don't remember that that was taken from space. It was one of the missions that Joby was involved in, and a number of us were involved in it. You use your GPS. I mean, every time I look at my iPhone and I'm lost, I try to find where I am. People don't remember that that's coming from satellites. So already the space industry is, in many areas, we have a major space industry going on. And then June asked, what are your thoughts of the amateur astronomer contribution to the Juno mission? Are there plans for continuing community involvement with future missions? Yes, I think amateur astronomers could play a major role in all the mission because we get tremendous amount of data. And as I showed you the picture earlier, you have billions of stars in the sky. And even if you get the smartest and the best scientists, there is not enough of them, to actually be able to look at all the data, to actually examine all the phenomena. So I think having amateur astronomers is a great thing to continue. And I hope JPL, I mean, I'm not controlling it anymore, but I hope that that will continue in our future missions. And the last one from Param, what opportunities does JPL have for quantum physicists and astrophysicists? Clearly, we have a lot of opportunity for astrophysicists. Quantum physicists, too, because people ask me, what should I study to be able to work at JPL? And I tell them, we hire people from every background. Every technical discipline, every scientific discipline. As I told you earlier, we have 6 artists who work at JPL, people from business background, outreach, communication, education, from all the disciplines that you need that, because you can never tell where the next discovery will happen. So it could be somebody, a quantum physicist, and they come with idea about quantum computing, putting a new version of computers in our spacecraft versus the computers we use today. So clearly, I usually tell people, don't try to be too specific on what you study. As long as you are in a technical discipline, almost any technical discipline, you will have opportunity to work at a place like JPL. So I see we have 2 more, so I'll take 2 more questions, and I'll let people go, and I'll stick around in case people want to ask more questions.
Well, it's been an honor to hear you talk. I have a question about kind of the development of the space industry in sort of like a holistic way. So with technology, development of technology tends to grow exponentially, like it grows on itself with stuff like Moore's Law, especially in computing. Whereas, the space industry isn't just a technological beast, it's political and it's tied to money. So when you were director, did you see a pattern of things tending to speed up exponentially, or is it kind of like bounce around depending on political climate or some mixture?
Now, when you say there is not enough money, I mean, what do you mean? What did you mean by that? You mean the funding to play things like what we do here? Well, I'm not sure I can answer your question exactly, but let me give you a perspective from my experience as a director here. People are very fascinated, with exploration, even in Washington. It might be hard to believe, but that's true. And I know it's being recorded and transmitted. But I found that in general, people believe that technology really is a great investment for our country, almost no matter what technology you do. Almost never did I get a question when I used to go and talk with congressmen and senators, or people saying, well, why should I give you the money? What are you going to do for me tomorrow? They always think about that in the long term, by investing in technology and education, there will be a benefit, from it. And I always give them one simple example. I'm sure you all have an iPhone, and you have a camera in your iPhone, on it. I tell people, do you realize that the focal plane in that camera was developed at JPL for our telescope? We had no idea that it could be used in an iPhone. But then entrepreneurs took that technology and developed it and made a whole business, out of it. So basically, there is a strong belief, and I think that's great in our country. There is a belief that by investing in technology, you will get benefit from it. It might not be tomorrow. It will be maybe 4 years from now, 5 years from now. When I was your age, we used to send memos We had no idea about email and all of this thing. We didn't have any of that stuff. I still have, when I clean my office, I still have stacks, of memos that we used to send around and communicate. But somebody invested in that technology, and now you use the internet. You can't even think of sending a memo, these days. So I don't know if I answered your question, but I think from what I grabbed from what you intended to do.
Thanks so much.
Okay, we'll do one more, and then.
Stephen Hawking said that.
Can you turn down the microphone? Yeah, sorry. Yeah.
Like this? Okay. Stephen Hawking made some comment about, or some prediction, that for humankind to survive, we would need to colonize somewhere. I'd like your opinion about that, please.
Okay, I think I'm not going to debate with Hawkins. I mean, he's a pretty smart guy. But I think before we start thinking about finding another place to go, we ought to be thinking about how we protect our planet. Because I think I'm a strong believer that we are a smart species. And sooner or later, we are going to realize that we might be doing damage to our planet. And I'm optimistic that actually we say, look, we really need to do a better job at managing our planet and have more peaceful relationship, care about our environment. I mean, it might sound strange considering what happened this morning, but I think at the end, I have a strong confidence. I'm an optimist. So I have confidence that our species will realize that we better do a better job at protecting our planet and keep it a good place. Now, that doesn't mean we shouldn't explore and go to other places, but it doesn't have to be because we are worried that we are going to blow ourselves up here or blow our planet. So I think I put more priority on protecting our own planet. Okay, thank you very much, and thank you everybody for coming.